Let's review the equations we used in calculating the confidence interval when we knew the sigma of the population. We started with the equation for z, the relative standing for the standard normal distribution. We then used this inequality to show that the population mean is somewhere between the sample mean minus the error and the sample mean plus the error. Using a bit of algebra, we then showed this equation is equivalent to the first equation. And since the equivalent parts of the equations are equal, we have the expression for plus and minus e, the error. The equivalent equation for t is this. Notice the similarity to the equation for z. Using the same algebra, starting with the inequality, we would get this result, making the equation for the error very similar to the equation we used when we knew the population standard deviation. In summary, to calculate the error when the population standard deviation is unknown, we will need the sample mean, the standard deviation of the sample, and the sample size. The only necessary value remaining is t, and we will need to set up an example first in order to determine its value. We'll keep these two equations here while we set up our example. Remember, we have a population where we do not know the mean or the standard deviation. In order to learn what we can about this population, we take a sample. We choose a sample size of 31, and these 31 samples have a mean of 30 and a standard deviation of 5. The degrees of freedom is necessary when working with the t-distribution and is always one less than the sample size. We have set a confidence interval of 95%, which means alpha is equal to 0.05. Remember, alpha is always 1 minus the confidence interval. Let's now take a look at this graphically. This is the graph of the t-distribution. Like the standard normal distribution, it has a mean of 0 and the equivalent of a standard deviation of 1. It is important to note that this is not a normal distribution. The shape of this distribution will change with the sample size. We will explore the impact of this later in the video. Alpha is then divided equally between the two tails of the distribution, with 0.025 in the left tail and 0.025 in the right tail. In order to calculate the confidence interval, we need to determine a value for the error. And in order to determine the error, we need a value for t. The value of t we need is the t that has 0.025 area in one tail, or 0.05 area in two tails, and a degrees of freedom of 30. The parameters of the problem are repeated here. The confidence interval of 95% or 0.95 is found in this column. This is the same column that corresponds to an area in one tail of 0.025 and an area in two tails of 0.05. The value of t we need is in this column. The rho is determined by the degrees of freedom, which is 30 for this example. The intersection of this column and this row is where we get the value of t, and it is 2.042. With the value of t, we now have all the values we need to calculate the error, and a 95% confidence interval for the value of the population mean. First, let's calculate the error. For t, we use the value we just retrieved from the table. For s, the standard deviation of the sample, we use the given value 5. And for n, the sample size, we use 31. The calculated value for the error is plus or minus 1.834, which we will also store here. Now that we have a value for the error, we can calculate the actual confidence interval. For the lower limit of the interval, we take the value of the sample mean and subtract from it the error for a result of 28.17. For the upper limit of the interval, we take the value of the sample mean and this time add to it the value of the error for a result of 31.83. In summary, we are 95% confident that the mean of the population is between the values of 28.17 and 31.83. As with the standard normal distribution, the magnitude of the error will increase as the sample size becomes smaller. Also, as the error increases, the confidence interval becomes larger. We should also note that as the sample size changes, the shape of the t-distribution changes, affecting the area in the tails of the distribution. As we bring the sample size back to 31, notice that the value of t changes also. This is due to the fact that t is also a function of the degrees of freedom, and emphasizes the fact that each degree of freedom has a different t-distribution.